In Module 1B, we're talking about the sky and the seasons, and in this section, we're going to talk about the sky. So this is an introduction. Oh, some basic definitions with this very not to scale picture here, just to make sure you know the moon orbits around the Earth, and the Earth orbits around the sun. A definition of the year, that's the time it takes the Earth to orbit the sun one time. And a day is the time it takes for a planet, such as Earth, to rotate on its axis one time. The directions are all about that rotation, and the east side is the direction where things rise. Okay, you know what rise means? That means when things come up above the horizon as seen by an observer. And another word that you may have heard is the zenith. That's the point directly over your head wherever you happen to be on the planet. Few distances and things that you should be aware of, because we can't use the usual inches, miles, kilometers. We talk about an astronomical unit. That is the average distance from the Earth to the Sun. It's about 93 million miles from here to the Sun. Light year is a distance. 1 light year is the distance that light can travel in a year, and that is a huge distance. Don't be confused about it being a unit of time, but it is the distance light travels in a year. Other distances in light travel time, well, light from the moon, 1 second. Light from the sun, 8 minutes. So 1 AU is 8 light minutes long. Nearest star is about 4 light years away, so it takes 4 years for the light to travel to us from the nearest star. Okay, not our sun. I know technically it is a star, but I mean the nearest star to our sun.
How long does it take for the Earth to go around the sun?
Well, a day.
Yeah?
24 hours.
24 hours?
What do you reckon, cuz?
Isn't it 24 hours?
Obviously a day, yes.
A day, I hope.
I know it takes 90 minutes for the space station to go around the Earth.
360 days.
No, 1 day. Is it 1 day? I don't know. What is it?
That's 1 year.
Oh, like a year.
A year.
1 year.
12 months.
12 months?
365.
365.
365.
365.
365 days.
Yeah, I'd agree with that.
365.
It's somewhere between that. It's not quite precise, is it?
365 and a bit days.
It's nearly 300. It's 365.25.
5 1/4 days.
Hey, the Earth doesn't take 1 day to get around the sun. It takes like a year.
Now you're going to think I'm being picky about this, but we need to be specific about what's rotation and what is revolution. The Earth's rotation is what causes all daily motion, the rising and setting of the sun and everything else. The rotation is its motion around the axis that goes from the North Pole to the South Pole. So far, so good. But there's a similar word, revolution, and that's for an object orbiting around something else. So the Earth revolves around the sun. Here's some examples. You're frequently going to hear something like a planet rotates around a star. But it's not really a full rotation. It is going around it, but it's not rotating on its axis. So you should say a planet revolves around a star. You can get around it by saying the planet orbits around the star, and then there would be no objections at all. So as Earth rotates, objects rise and set, and you can see on this animation it looks like the objects are going around the Earth, but you know that rotation is due to the Earth, that the rising and setting is due to the Earth rotating. Notice up in the north side there's a star that never sets. That's a circumpolar star, and there's one that's at the south, near the south celestial pole, and that one never rises. The gray area is the horizon of that observer, so he can't see anything below the horizon. Now you see that star set in the west, then he can't see it until it rises again in the east. This is the rotation, and you notice that because he is not at the North Pole, that horizon, the gray horizon, is tilted compared to the rising and setting. In fact, when the star rises, it doesn't go straight up. It rises at a slant. And for an observer in the North Hemisphere, the Northern Hemisphere, like our yellow person there, the stars are rising and they swing not overhead, but they swing towards the south a little bit as they rise.
The apparent motions of the stars in the night sky depend on your position on the Earth's surface. At a northern temperate latitude, the stars rise in the east and set in the west, and they travel on slanting paths across the sky.
This picture shows the entire western horizon from the north to the south on the left, right and the left. Can you see how the stars in this time lapse are rising straight up, or in this case setting straight down? That's an indication that this has to be a picture taken at the equator. At the equator, the stars really do rise straight up. The ones that rise due east will go straight overhead, and they will go over the observer's head and set due west. Notice the sort of curvature that you see on the left and the right. The stars really do go around the North Star and where the South Star would be, the North and South celestial poles that we'll talk about more in the next unit. So with the rising and setting motions, at the equator they rise straight up. In the Northern Hemisphere they slant to the south. And if you were actually at the North Pole, the objects would go around and around the North Star, never rising or setting.
Some stars are visible throughout the night as they orbit the North Celestial Pole. They are called circumpolar stars. If you were positioned at the Earth's equator, stars would appear to rise directly out of the east and set directly into the west. The North Celestial Pole would be down on the horizon. That represents the region around which the stars are rotating in the night sky. If you move to the pole of the Earth, the North Pole of the Earth, the North Celestial Pole will be directly overhead. Imagine yourself standing on the top of a spinning top, staring upwards. All of the stars would be circumpolar. Those near the horizon would be orbiting parallel to the horizon. And all stars would appear to circuit around the North Celestial Pole or the star Polaris, which would be directly above your head.
These are two objects, and it's a picture taken in the Northern Hemisphere, and you see from the time-lapse part the direction of the slant. And the slant is from the left to the right. You're in the Northern Hemisphere. Is this looking east or west? Well, let's think. If you're looking east, that's where things rise. And in the Northern Hemisphere, when they rise, they swing to the south. So they have to swing to the right. That's not what's going on here. So this is not rising. It's not looking to the east. Well, does it work for the west? If we're looking to the west, as they set, they should swing down towards the north. And yes, that's exactly what we're seeing here, is that we're looking towards the west, and the objects are slanting towards the north as they set. This picture of the sky shows Saturn, the Moon, Mercury, and a line drawn across the sky called the ecliptic. The ecliptic is the sun's path across the sky, and it turns out the planets and the Moon are always near the ecliptic. Here the ecliptic plane is shown. The ecliptic plane is defined by Earth's orbit, so you can think about Earth going around the sun, or you can think about being on Earth looking toward the sun and seeing where it moves against the background stars. That plane of the ecliptic is defined by Earth's orbit, but all of the planets are approximately in that plane of the ecliptic. This little drawing is pretty accurate for giving the idea that all of the planets are in the same flat plane. As Earth orbits around the Sun, we keep getting a different view of the Sun against different background stars. So because of Earth's motion, the Sun is seen to move across the background stars. That's the Sun moving on the ecliptic, and the constellations that it goes through are the zodiac constellations that you see labeled in this picture. Because our solar system is flat, the only place that we see the planets are also near the ecliptic. The ecliptic, Sun's path across the stars, it's due to the Earth orbiting around the Sun, so obviously the Sun comes back to the same place 1 year later. The ecliptic is centered right in the zodiac constellations. They take up a lot of room, but the zodiac goes right down the center. So the Sun is always in a zodiac constellation, and the planets are always near the ecliptic, and the zodiac constellations were actually given significance because the location of the planets always in those constellations. There is one other constellation, Ophiuchus, one of the constellations that actually the Sun and planets might go through, but that's not one of these official zodiac constellations. It's just that the constellations don't have even little boundaries, and Ophiuchus overlapped, and there are actually some people who were born when the Sun was in that constellation. In summary, Module 1B, Part 1, the Sky Introduction, we've learned that at different latitudes you'll see the stars rise differently. In the northern hemisphere they will rise at a slant, swinging towards the south, unless you're at the North Pole, in which case they will move around the sky, never rising or setting. At the equator they would rise straight up. We also learned about other sky motions, and we are going to go on and talk about the celestial sphere and talk more specifically about the North Celestial Pole and where the ecliptic is on the sky.